Today I'm going to be talking about how we're using computational structure searching to find the next lithium-ion battery anode. So I'm going to be taking a look at this from kind of a pretty broad viewpoint and then hone in on just one or two results that I've gotten throughout the course of my PhD. But to kind of give you a flavor of what we're trying to do, I just want to take you through a bit of the history of lithium-ion batteries. So today we're going to be starting with discussing why we're actually looking at lithium-ion batteries in the first place, and then a bit on the methods that I've used throughout my PhD, which are known as structure searching methods to identify new battery materials. And we'll also discuss why we might want to identify new battery materials. And I'll present a few results to you. And then as a little teaser at the end, I'll just give you a little bit of an idea of kind of where this field is going, what's coming next, and kind of where we can go from here. And of course, I need to acknowledge my funding sources at the bottom, the millions of hours of compute time that I've used over the past few years, along with Gates and Winton. So why are we looking at lithium-ion batteries at all? Well, you might know, or you might not know, that the Nobel Prize in 2019 for chemistry was given to the lithium-ion battery, and the group of three men, Stanley Whittingham, Akira Yoshino, and John Goodenough, who actually discovered the lithium-ion battery. And these batteries are especially special for a couple of different reasons. So you might have also heard of a lithium battery. And there's a big difference between a lithium-ion battery and a lithium battery, or a primary battery, in that lithium-ion batteries are special for the fact that they can actually recharge themselves. So the ion part of lithium-ion is all about ions shuttling back and forth between the anode and the cathode so that you can charge and recharge your battery. With the added bonus that lithium-ion batteries in particular have a really high energy density, so you can use them for a few of the things that you might know so far, like electric vehicles or potentially gigafactories. But that's a little bit down the line, and the electric vehicles that we have so far can't exactly travel as far as we'd like them to. So lithium-ion batteries were, one of the greatest achievements of the 1990s, and Sony being able to actually produce them at the rate that they were with cheap enough materials was a real advent, and kind of brought about really the technological revolution of the last 20 years. So it is definitely fair that they finally got the Nobel Prize in 2019, because I mean, probably sitting around you right now, if you're watching this on a computer, you already have, hundreds of lithium-ion cells in your computer, in your phone, and anything around you that can be charged. So lithium-ion batteries are really important, but they obviously have some downsides. So one of their downsides is, like I say, energy density. In the 1990s, when they were created, the energy density was really great for the portable electronic applications that we wanted them for. But now, as we're looking towards 2050, looking at that goal that we've set for ourselves, we need more energy storage, and we need to have batteries that can charge for weeks on end, and we need to have batteries that can power an entire grid system. And in order to do that, we're going to have to find something else besides a lithium-ion battery to do this. And then, of course, we come to the issue of safety. Lithium-ion batteries are notorious for lighting on fire. Samsung made that famous in 2017. You might remember you weren't allowed to take the Note 7 on any airplanes after that time. And this is, obviously a real disadvantage of batteries, especially in Tesla. If you get into a car crash, it's really important that the batteries that are in there are safe, and it's not going to be the battery that causes further complications. And finally, and possibly most importantly, is sustainability. A lot of the ways that we make lithium-ion batteries, a lot of the materials that are used in lithium-ion batteries, like lithium, like cobalt, are not exactly renewable resources. And cobalt especially, the price has skyrocketed in the last 2 to 4 years with the number of lithium-ion batteries that have been produced. In addition, there are estimates that in order to produce the amount of lithium that we would need over the next 20 years by 2050 to actually kind of match our energy demands, we'd have to be increasing the rate at which we're mining lithium, mainly in South America, by about 100-fold. So this just really isn't something that's possible. in a large scale application, and it's probably also not good for the environment. And our goal here is to make a better environment. So we have all these problems with lithium-ion batteries, and you can tackle them in a lot of different ways. But the main way that we're going to take a look at tackling these problems is through new materials. So for each one of the problems that I described previously, one simple thing that you can do is take a different material, a different element from the periodic table even, and put it into the lithium-ion battery and see if it improves its energy density. In the top, one of the materials you could swap out would be taking the carbon anodes, taking those out and replacing them with silicon. That gives you a much higher capacity. On the safety side, one of the issues with safety is mainly the liquid electrolyte and the fact that it's liquid and that it's flammable. So you can take out the liquid electrolyte and replace it with a solid electrolyte, something like LGPS, which is what you see here. One of our labs uses LLZO. And these solid state materials are a lot more safer than the liquid and a lot less flammable, i.e. not flammable at all. And finally, sustainability. And this is a real key one, especially with lithium stores dwindling as we speak. You can take lithium out of the lithium-ion battery and replace it with something like sodium or potassium or whatever the next element going down the alkali metals of your choice is from the periodic table. And of course, this seems like a really simple solution. We can take the materials we have in our lithium-ion battery, fabricate new ones, and make a higher energy density, safer, more sustainable battery. But of course, each of the new materials has their own caveats. So it really is a balancing act here between identifying a new material to create the class of sustainable next generation batteries, while also maintaining their cost, their safety, and the actual power that they output. So what I'm going to be talking to you about today is how we use totally computational techniques, so modeling, not going into the lab at all, to try and identify what types of materials we might be able to use in lithium-ion batteries. So the method by which we do this is known as structure searching. And structure searching is a really interesting technique, which has been developed kind of over the last 20 years, I would say. So in the periodic table, you can combine any two elements, any three elements of your choice, sort of, and make different materials. And so online, there are a lot of different databases of materials that already exist in the literature. One of these that I'm showing you some data from here is the Open Quantum Materials database. So there are databases out there that have hosts of information about different materials that exist. And so one thing you can do is mine through these databases and try and look at potential new materials that might suit the needs of your lithium-ion battery that you're looking for. So what you see in this plot here is we've looked through the Open Quantum Materials database. We've tried to identify any material with lithium or sodium in it because we want something that works in a lithium-ion or sodium-ion battery. We've identified any material that has phosphorus in it because one of the things that we know is that phosphorus is the potential for replacing graphite at the anode because it has a much higher capacity. And then we've added in any other element that has a material or matches with those. And what we find actually is that there are hundreds of thousands of materials on the scale of hundreds really in that database alone that fit those criteria. So they have high capacities, they have low volume expansion, so they are potential candidates for a new battery material. And that's really interesting. And so we can look at these materials and we can take it one step further and say, well, actually, a lot of these materials have already been tried and tested experimentally, and some of them don't really work or they have their own difficulties. So what if there's a new material, one that's not in the database? How do we actually find that material? So to do that, we can take our database as a starting point and do what I said we were going to do this whole time, which is computational structure searching. So we start from a set of atoms of our choosing. In our case, we're going to be looking at lithium, phosphorus, and some other materials. We can put them into a box in random locations and relax them using something known as density functional theory, and then repeat this process hundreds of thousands of times in order to try and identify what types of structures are stable experimentally. So why do we want to do this? Why not just go into the lab and make hundreds of thousands of materials? Well, if there's any experimentalists on the call whatsoever, they probably wouldn't want to do that. So if you're going to end up synthesizing a random stoichiometry of atoms with a random unit cell size with some sort of random synthesis technique that we haven't figured out yet, it's just a bit too many variables to actually identify a material in an efficient way. So random structure searching, not just for battery materials, but for any material, is a really good starting step to kind of getting experimentally where you want to be in identifying a new material. So this is the process that we're going to use to look at specifically battery materials. But like I said before, you could take this and apply it to really any material science problem that you have if you're looking for a new material. You can even look at materials at high pressure and high temperature, as we're going to see a bit later on. So does it work? The answer is yes, it does work. What you can see here is we've done this on a different study of sodium phosphides. So this is saying we'd like to have a sodium-ion battery, and we'd like to use phosphorus as the anode. So what kinds of materials, what kinds of structures might we expect to see in our sodium phosphide anode material? And what you can see on this plot that I've shown you, and this is going to be really similar to some other plots that I'm going to show you later, is that we have our different compositions of sodium and phosphorus on the x-axis, and then on the y-axis we have their formation energy. So the lower a material's formation energy, the more stable it is, which means all of those materials that are on that green tie line here, these are going to be all materials that are stable experimentally, or predicted to be stable experimentally. So this is kind of a way in which we can assess the difference in energy of each of these materials and see which one works. So we have this process, we know it works. Let's do one quick specific example of actually applying it to a lithium-ion battery material. So this is the project that I've done over the past few years. So I've taken a set of materials known as the copper phosphides, and I've attempted to search for a new material within that phase diagram that has a higher capacity than graphite. So why are we looking at the copper phosphides? Just to give you a bit of a background, copper phosphides have been used previously as lithium-ion battery anodes. However, they each have their own different set of problems. So Cu3P was used as an anode material, but it has quite a low capacity. It's still higher than graphite, which is good, but it's still not as high as we'd want it to be. And for reference, graphite has a capacity around 372 milliamp hours per gram. CuP2 has a much higher capacity, almost 1,000 milliamp hours per gram, but after about 2 cycles, it ends up degrading. So we'd ideally like to find a material with a stoichiometry that sits somewhere between these two. So we get a bit higher capacity than Cu3P and a bit less degradation than CuP2. And this is exactly the type of problem that computational structure searching is going to be perfect at solving. So we've gone through and we've searched for almost 20,000 different structures of CuP stoichiometries. And what you can see over on the left is we found a fair number of structures that were low in energy. So anything on this Hall tie line is considered potentially stable. And we see that we have one new structure here, Cu2P, and very advantageously, it lies exactly in the stoichiometry range that we set out before. So it has lower copper content than Cu3P, which means it's going to have a higher capacity, and it has a higher copper content than CuP2, which means it's probably going to be stable when you cycle it with lithium. And we've done one more extra trick here to actually say okay, these structures are stable, but one thing about the theory that we've used in this plot over here on the left is that it's at 0 Kelvin. And 0 Kelvin is quite cold, i.e. Nothing's ever reached 0 Kelvin before. So maybe this isn't exactly telling us what types of materials we'd want to use in a lithium-ion battery. We can apply a few other expressions onto our expression for the ground state energy of these materials to end up calculating the Gibbs free energy, which means we can now look at these materials at high temperature. So we turn up the heat on this plot on the left, and you get the plot on the right, where we actually see that this Cu2p material remains stable all the way up to 600 Kelvin. So this is really good because this means not only is it a new material that we've predicted, but also it is actually likely to be synthesizable, which is what an experimentalist wants to see when you tell them, oh, I found a new material. They're going to say, yeah, but did you really? So it is stable at high temperature, which is really good. And now the final question, is it actually a good battery material? So it probably exists, but does it exist and work in lithium-ion batteries? And the answer is, again, yes, it does. So on the left, we have an experimental voltage profile, which gives us an idea. If you follow this black line from left to right, you can imagine that we're adding more and more lithium into the system until we have added the total amount of lithium in that we possibly can. So graphite would sit here around 350, 370 milliamp hours per gram. And what you can see from the Cu2p phase is that it has a capacity which goes beyond 372, all the way up to over 500 milliamp hours per gram, which is really good. And one of the things that we know experimentally from this Cu3p phase, that yellow line, is that we'd expect this to actually be a really cyclable material. So you can cycle it more than just once and insert lithium ions, take them back out, and do this multiple times, and the battery remains stable. And then over on the right, we can take a look at volume expansion. So I said before that CuP2 wasn't exactly a good battery material because it would degrade. And the main reason it would degrade is because it has a really high volume expansion. And so essentially when you insert lithium ions, the whole cell lattice just explodes to a point where you can't actually insert and reinsert lithium atoms, and you end up getting electrolyte degradation, etc. And what we see with Cu2p is that it has, almost 2/3 the amount of volume expansion as these other high phosphorus content copper phosphide materials. So that's a really promising sign, which suggests that it's not going to expand either. And so this is really good. We've identified this material, Cu2p. It probably works in batteries. It's definitely stable up to high temperatures, and we haven't wasted any experimental resources trying to identify these new materials. We can now just go to an experimentalist and say, can you try and make this copper 2 phosphide material? And so that's what we've done. And so everything I've talked about up till this point is using density functional theory, which I mentioned only briefly, but kind of is the workhorse of all of the work that we've done so far. And density functional theory, again, won the Nobel Prize in the 90s, I believe, for being basically almost an exact to a limit theory for identifying the energy of materials at the quantum mechanical level. But it's a very expensive theory. And so one of the things that you'll see is a lot of structures that look like this. And I mean, you can count the number of atoms in this structure on your hand. There's maybe only 20 atoms or so. And obviously a real battery material, real material systems have millions of atoms. So ideally our models, we'd really like them to be, at least hundreds of atoms, if not thousands of atoms, or even bigger. And so where do we go from here with identifying materials beyond just these crystal structures that we've predicted so far? And the answer, which you might have guessed by looking at this picture up here, is of course machine learning. So we can take all the structures from those databases that I've talked to you about before. We can take all the structures from studies like this one that I've done, studies like my copper phosphide study, and use the knowledge that we have from density functional theory to actually train a new machine learned theory to calculate the ground state energy of materials. And there's some initial work coming out from the Archwith group on, and the Sater group as well, on machine learning these same types of plots that I've been showing you before. And if you remember, I searched for around 20,000 atoms, 20,000 structures, sorry. This machine learning algorithm, with about 1/10 of the computational cost, searches for 500,000 different structures. So it really is kind of the future of where this field is going. And ideally is really what we're going to be able to use in the future to not only model one part of the battery, but hopefully model interfaces in the battery, and maybe eventually at some point the actual chemistry of the redox that occurs throughout the whole thing. So that just gives you a little bit of a taste of what's next. But with that, I'm just going to leave you with the thanks, and just point you to something kind of cool that I always like to show people is in that paper that I had shown you earlier with those results from the copper phosphides. I've actually put all of the information there online. So if you're even remotely interested in seeing kind of how we actually did all those calculations, or playing with the data yourself, it is actually all available on GitHub and through Binder. So you can play with it yourself, make new graphs, tell me where I did something wrong, and kind of go through the whole thing yourself. But with that, I'll just say hopefully you've learned how we can use computational structure searching to identify new battery materials, and thank you for your time.